Hi, it's high time I made another video, and this time I wanted to do something a little bit different. A few people have asked me in the past how I go about porting cores to the Turbo Chameleon 64, so I thought this time I'd go step by step through the process and show you how it all fits together. So the core I'm going to be porting is the VIC20 core from Mist, and yeah, I'll go through that step by step and show you how I incorporate it with my own framework, Demystify, for a kind of compatibility layer for Mist cores. I'll show you why that's necessary first of all. So this is a broad outline of how FPGA cores work on the Mist platform, where we have the FPGA itself, which is the same FPGA as is found in the Chameleon, but also on board is a microcontroller which deals with talking to the SD card and talking to the keyboard, mouse and joysticks. Now on the Chameleon 64 it's slightly different. We don't have the microcontroller, or at least technically there is a microcontroller on there, but it's really only there to get the core running on the FPGA in the first place, and it doesn't really play an active role thereafter. So we have the FPGA talking directly to the SD card and talking directly to the keyboard, mouse and joysticks, which means that to get a Mist core working on the Chameleon we have to replicate the functionality of that microcontroller somehow, or we have to rewrite the core so that it doesn't need it. So the approach I normally use is to include a soft CPU on the inside the FPGA core alongside the guest core that's being ported, so all the microcontroller stuff happens in there, and as long as there's room in the FPGA for both, then that works out quite nicely. It can be a bit of a challenge because the firmware on the Mist microcontroller is somewhere in the region of 240k, and the FPGA's internal RAM is actually less than 80k, and obviously the guest core needs some of that for its own purposes, so it's not always easy to get it to fit. I've basically implemented a very small subset of the Mist firmware functionality and got it down as small as I can, and for most cores I can run it from 12k. So first of all let's check out a copy of the guest core we want to use. So I'll just highlight that, go to a shell window, and we want to do git clone like so. Now we'll enter the directory we've just checked out. We'll do a git submodule update --init --recursive. I spelled recursive right that time, that doesn't often happen. There we are. So now we'll open the Mist project in Quartus. And we'll build it just so we can take a look. So while it's doing that, I should explain that if you want to build for the Turbo Chameleon 64, there are two versions of the hardware. Version 1 hardware has exactly the same FPGA as the Mist, the Cyclone 3 with 25,000 logic elements. The version 2 hardware has a Cyclone 10 LP, same size, it's basically the same thing, just in an updated package. So the difficulty is that Quartus, the latest version of Quartus no longer supports Cyclone 3. The last version that supports that is 13.1, but 13.1 doesn't support the Cyclone 10 LP, which means you need more than one version installed. Now I tend to use, as I say, 13.1 for Cyclone 3. I generally use version 18 for Cyclone 10 LP for the V2 hardware. No specific reason why it's 18, it's just that when I first needed to build for Cyclone 10 that was the latest version at the time, and since it's such a large download it's not something that you tend to update unless you have to. So yes, Quartus 13.1 for the version 1 hardware, and 18, I think it was about version 14 they introduced support for that one, but as I say, I tend to use 18. So while it's doing that, the thing we need to do is check out a copy of my compatibility layer as a submodule. So if I go here, let's submod add, and then the URL. We'll now have a demystify folder. I'm going to demystify folder. I'm going to repeat the submodule update init recursive line because demystify does have its own submodules. It has the 832 CPU, my microprocessor project, and some standard modules that you need for the Chameleon. I have a collection of those which I can include in projects, save me copying them around here, there and everywhere. Helps keep everything in sync. Okay, the mist core has finished building. So first of all, let's have a look at the fitter report. Make sure everything's going to fit. So we have 7,981 logic elements in use on the mist out of 24,624, and that's the same number we've got available on the Chameleon, so there's plenty of room for the compatibility layer. That needs about 2,500, so loads of room for that. We also need to check the resource section and have a look for M9Ks, because as I said, the firmware, generally speaking, I get it down to about 12K, so we need, well, each M9K is 9,000 bits of internal RAM, and it's basically 8,000 bits plus parity bits, so it's effectively 1 kilobyte of RAM for each one of those. So we need 12 of them for the firmware, and yes, we have more than 12 available, so we should be good to go. The other thing we need to look at is clocks. So if we look at clocks in the TimeQuest report, you'll notice that we've got a red line down there, unconstrained paths. We can safely ignore that for the time being. We'll sort that out later, probably the next video. But clocks themselves will show that we've got a clock 27 incoming to the FPGA. It's a base clock at 27 megahertz. We've got the SPI SCK, which is also a base clock coming into the FPGA. That's actually the clock for communicating with the microcontroller. And then we have two PLL generated clocks here, one of which is 35.49 megahertz, the other one is 32. Now the way these cores tend to work, as I say, there's that 27 megahertz clock available incoming to the FPGA. Almost no core uses that directly. They're nearly always fed into a PLL to be converted to a different clock frequency, something more convenient for the core itself. And what that means is that with the compatibility layer, I don't actually need to worry about creating a 27 megahertz clock. What I do is just feed in whatever the board space clock happens to be, and then create a board specific version of any PLLs. So on V1 hardware, even though it's called clock 27, the signal will actually be 8 megahertz because that's what the onboard clock generates on V1 hardware. So I'll create PLLs that create these clocks from the 8 megahertz base clock. And likewise on V2 hardware, exactly the same principle, except the base clock will be 50 megahertz. So yeah, that's the basic principle. We also need to have a look at the top level and see how the clocks are defined. Now this is actually awkward. Nearly always the MIST core will just have clock 27 with nothing after except the comma, or it will have 1:0 there, like that. And what that basically means is you've got two clock signals incoming. I think it's a positive and negative version of the same clock. Generally speaking, only the bottom one's ever used. And I've not actually seen it done like that before with just an array with a single element, and that's actually going to cause us a little bit of grief later on, but I'll show you that when we get there. The other thing we need to check excuse me, is the SPI DO line here. Make sure it's set to an output. Some cores have that set as a bidirectional line, which makes life difficult. We have to work around that if that's the case. Yeah, for now we can ignore that. That's fine because it's only set to output. So let's go back to our shell window. So the Demystify project has a load of template files in there which are going to help us out. So the first thing I'm going to do is copy Demystify templates makefile to our top directory, and I'm going to edit that. The only change I'm going to make here is convert the project name to VIC20. I'm now going to type make, and it will whinge at me that I haven't created a site.makefile yet. Now, what I've basically done here, site.make contains anything specific to the computer I'm running it on, and the idea is basically that if you've got more than one person working on a project, they're going to need different site settings. So if you just edit a file that's in the repository, then you're going to end up with a commit war. So what we'll do is just copy site.template to demystify site.make, and then we'll edit that. And you see we've got a list of boards there that we can build for. Those are, if we add a new board, we just add it to that list and it will get automatically built. We can also override that. Q13, that's just a variable set to point to version 13 of Quartus, or 13.1 in this case. Q18, again, if you've got a different version, you just create a variable, or you could even just edit this one, it doesn't really matter that much. ISE for Xilinx devices, not yet supported, so you can ignore that. And then down here, for each FPGA family, which version of Quartus or which utility or which tool should be used. So that's how that works. Again, it's really just a case of setting those paths and then you should be good to go. So now if I run make again, it's now going to build the compiler for the 832 CPU. If you've ever tangled with GCC, then your shoulders are probably sagging at this point because you'll be expecting a long wait. But luckily we're not actually using GCC, we're using VBCC instead. So at this stage it's going to ask a bunch of questions and we can just accept the defaults, assuming we're building on a fairly standard Linux system. So we'll just step through that. Building the compiler, done. Building the assembler and linker, done. Building some demo projects and tests and making sure they all work. So there we are, it's built the compiler. It's now paused because we've got no firmware directory yet, so let's fix that. Make dev firmware. Now we're going to create an empty overrides.c file in firmware. And we're going to copy the config.h file from the templates into firmware as well. And let's have a look at that, see what we need to change. So here we are, here's the config file. We probably don't need to change anything for the moment. So we have PS2 mouse. Well, a VIC20 is not going to have a lot of use for one of those. It's not going to have a lot of use for a CD-ROM either. Disk images, yes, we do want that because we're going to have D64 support, so we'll hash define those instead of undefining them. We won't define bookmarks, that's a speed up thing basically. It's just to make it quicker seeking from one end of a file to another in a fat file system, and the files we're using for the VIC20 are going to be small enough that that's really not important. We don't need keyboard based joystick emulation. We probably don't need key events because I think if this is similar to the C16 core as I think it will be, then we can connect the PS2 keyboard directly. But I'll leave it there for now. And then yeah, two different ways of sending joystick events. We're going to use the newer of the two, which is set by default, so yeah, we'll leave that as it is. Now let's make the firmware. There we are. Now the size here, 2D38, that's the end of the BSS section in hexadecimal. There's also 512 bytes, so 200 in hex of stack to go on top of that, and provided that's the sum total is less than 3000, then we're under the 12k limit. We can have more than 12k if we want to, we just have to edit some variables to achieve that. So for now we'll leave it as is. So the next step is to get these project files into our guest project. Now we could copy them one by one, we could edit the mist QSF file. If I show you that, VIC20.qsf, we've got a load of definitions. This is what a Quartus project file looks like. It's just a TCL script, and that fact is exploited by Demystify when it comes to creating new projects. But at the end we've got, here we are, the files themselves. And again, we could just copy and paste those into a new file and do it that way. I'm not going to though. I've got a utility function in Demystify which I can use with Quartus sh-t, demystify scripts, qsf to qip, dash qsf, VIC20.qsf, .qip, VIC20.qip. There we are. Now a QIP file is basically just a file which pulls together a bunch of other files so that they can be added to a project as a single lump. So that's what we've got here. It's basically those lines straight out of the QSF, except each one now has a little clause there, file join QIP path with the file name of the component itself, just to make it all relative to the path the QIP file's in. So that's fine. Now this line, PLL27.qip, that we are going to have to generate specifically for each board. So I'm going to take that out of this, I'm going to comment that out, because this file will be common to all boards. Likewise down here, PLL VIC20, and likewise ROM reconfig PAL and ROM reconfig NTSC. We're going to need a board specific version of each of those. The ROM reconfig files, what that's basically about, the VIC20 can run in both NTSC or PAL, and it uses a different clock for the two different regions. And since the core supports both, it needs some way of changing the clock setup. So that's what those are for. So if I save that, I need to copy demystify template, project files and project defs. So if I look at project defs, there we are, that can be just left as it is. Project files, project.qip I'm going to change to VIC20.qip, and we can either use a customized version of the firmware where we override certain things. We will need to do that, so I'll use that version. But if we were definitely just using the standard firmware, we could use this instead. So I'm going to remove those two lines. Now if you're eagle-eyed, you might have noticed that the date in the bottom right hand corner of the screen just changed. And the reason for that is just that I'm patching in a little extra section here to explain something that I forgot earlier. There's something that the MIST core uses. Let's find it. There we are. Here we have include buildid.v. What that does is include a little header file which defines the build date, and that buildid.v file is constructed by way of a TCL script at compile time using a preflow script. Now I didn't notice that I'd omitted that initially, because the first thing I did was to build the core for MIST, which created buildid.v. But if you're not building for MIST, then we need to make sure that that file gets created. And the way we do that is through a preflow script. So we'll add that to the project files.rtl file now. First of all, a comment, preflow scripts. Now the one we want is called build id verilog.tcl. That should be all we need to do. Save that, and if I list the files there, you'll see the build id verilog.tcl file is there, and so is the build id.v. I mean, we could generate that as part of the make file, but since the mist core does it as a preflow script, we may as well do the same thing. So that's the correction. Now we'll go back to the original video. There we are. We need to copy a demystify config package.vhd file to the project root. Now this has definitions needed by VHDL top levels for the various different boards. It does things like define how much block RAM we're going to be using for our ROM. So as I said earlier, 12K in this case. We've got an 8K chunk and a 4K chunk. We can remap the joystick buttons if we want to by changing which bit each one maps to. Now here we're declaring the guest component, which is not guest.mist, it's VIC20.mist, or _mist rather. The clock, as I said, that's going to cause us some grief. These are the two options we've got to choose from, in standard logic or in standard logic vector 1 down to 0. Well, what we've actually got is standard logic vector 0, and it's not going to let us do that, so I'm going to use I'm going to comment out that line. I'm going to, well, the line that refers to DO being bidirectional, that's already commented out, so that's fine. SPI SS4 is actually only used when the SPI DO line is bidirectional as well, so I'll comment that out too. And there we are. That's everything we need in the top level directory now. So let's make a directory for the Chameleon64, and let's copy from demystify templates Chameleon64 top into Chameleon64, and we'll copy top.qip into Chameleon64. Now Chameleon64 top.qip, we have so as to say, we have the Chameleon top level, which is, we'll have to do a little bit of editing in that. Here, for most cores, we only have one PLL, and it's normally called PLL.qip. We've actually got two for this core. One of them is called PLL27, which is a really bad name for it on Chameleon because it's going to have an input of 8 MHz and an output of 32. And we have a PLL VIC20 file. We also have, let's see, we need, oh yes, those ROM reconfig files are going to have to go in here as well, so I'll just do it like this. ROM reconfig pal.quip, ROM reconfig ntsc.qip. There we are. So now what we need to do is copy those ROM reconfig files into Chameleon, because we're going to need to override those. In actual fact, we're not going to be overriding those per se, we're going to be overriding the configuration files that they read. So by far the easiest way to achieve that is to put a local copy in the Chameleon64 directory. So I think we're actually ready now to create our first set of project files for Chameleon64. So if I do make boards equals Chameleon64 init tells it just to create the project files. If I leave off init, it will do this and then attempt to compile it. I don't want it to compile yet because I want to open the project files in Quartus and just have a look at them, make sure everything's as we want it. So let's do that now. Let's open project, Chameleon 64. So here we are, this is the core ready for Chameleon. Now top.qip, we've got PLL27 is missing because we haven't generated it yet. Likewise PLL VIC20 is missing. If we open up the VIC20.qip and open up the mist top level, now let's have a look. Here's the VIC20 PLL, and you see it's saying we have needs to be 35.48 MHz for PAL systems and 28.63 MHz for NTSC systems. So let's create a PLL. We'll go to MegaWizard plugin manager, create a new custom mega function variation. We're going to call, we'll do the other one first, we'll do PLL27 first, PLL27.v. Now bearing in mind we're creating a PLL, you'd expect to find it under PLL, wouldn't you? Yeah, it's not there, it's under IO. Alt PLL, that's the one we want. Now, as I said earlier, the Chameleon's input, the version 1 Chameleon's input clock is 8 MHz, so we want 8 there. We just step through this wizard. We want dynamic reconfiguration. We want to create the optional inputs for dynamic reconfiguration. We're going to have to create a configuration file here in a moment, so let's step on to the next stage first. Now, what did I say we need? There we are. Now I can see it. We want 35.48 MHz in PAL. Well, that's the default, so I'm going to create the other one first, 28.63. Sorry, what am I doing? This is PLL27. We don't want. That'll be the next one. That'll be PLL VIC20. So for PLL27, we're actually generating a 32 MHz output. I suppose it's called PLL27 because on MIST that's the input clock frequency. But what it's actually doing is converting 27 MHz to 32 MHz. So on Chameleon V1, we need to convert 8 MHz to 32 MHz. So that's that, and actually we don't want dynamic reconfiguration for this one. So there we are. There we are, and now if we open PLL27.qip there, it now exists and it points to the files required to instantiate that PLL. So right, now I'll do the PLL VIC20.qip. I was getting ahead of myself there. Create a new PLL VIC20.v, IO, Alt PLL, and again 8 MHz input. Now this time we really do want optional inputs for dynamic reconfiguration. NTSC clock, as I said, is, oops, where did that go? Oh, there we are. Right, NTSC clock is 28.63 MHz. Now what I'm going to do there is go back a stage. Now I've just got to look up what the file's going to be called there. If we have a look, it's going to be called PLL VIC20 and NTSC.mif. PLL VIC20 NTSC.mif. I was just seeing what the MIST version of that file was called before I create a Chameleon version of it. Now we can do the other one, which needs to be 35.48. We'll take that out of there and we'll put PLL VIC20 pal.imf in that box, and it should generate that when it finishes. There we are. So let's just double check that it's done that. Okay, what have we got in here? There we have got a PLL, VIC20, NTSC and pal.mif. So that should be okay. So now we need to make a couple of customizations to the Chameleon 64 top level file. If we go down to where we instantiate the guest component, this needs to be called VIC20 mist, not guest.top. We only want to use the single clock entry there. We don't want the bidirectional workarounds for SPI-DO or SPI-SS4. And right, the only other thing we need to do is go into the top of the VIC20 file. I'd normally try and avoid editing the mist file at all, or the mist core at all, if I can possibly help it. But in this case I do need to change that. Clock 27 with a 0 in square brackets won't work, bearing in because I'm going to be referencing it from VHDL, and that causes a lot of confusion. So I'm going to have to remove the dummy subscript from clock 27. Looking for the instantiation of the PLLs, which is the other place that will show up. Oh, there it is. And last but not least, up here, there we are. Right, now let's try building it and see what happens. Now that change I've just had to make in the mist core, I would probably have to make a change to the pin assignments before building the mist core will work, so I'll have to remember to do that. Otherwise there's a very real chance it will build a core that doesn't work. So my goal with this is usually to have the core buildable on as many different platforms as possible. So if I've broken the mist core in the process of porting it, as far as I'm concerned, I've done it wrong. But we shall see what happens. So we haven't got any error messages yet, that's a good sign. So yes, that's running through the build process fairly smoothly so far. We'll see if we get any messages when we come to the fitter. The firmware doesn't yet attempt to, we haven't edited the firmware to the point where it'll upload the right ROM file, so the core won't actually work yet. What I'm doing at this first stage is just getting it to build successfully. But yes, it's succeeded doing the analysis and synthesis phase, so that's good. So while it's doing that, I could start adding some files to the repository. So git add, what have we created? We've created the VIC20.qip file, we've created project defs, project files, demystify config, and in Chameleon 64 we've created PLL 27 I would just use a wildcard here, but there tends to be actually I don't think there is. I'll see if I can get away with using a wildcard. No, I can't. There are PPF files in there which it doesn't like. It's just that the parent core, the VIC20 core, has those set in the gitignore file. So okay, in which case I'll do it manually. PLL27 BB PLL27.quip PLL27.v PLL VIC20 BB PLL VIC20 everything.mif PLL VIC20.quip PLL VIC20.v, all the ROM reconfig stuff, top.quip, and I won't add the VIC20 Chameleon 64 QPF and QSF files because they're generated by the script, so again you end up with a lot of noise in the commit logs if you add those. I forgot add from the git line. There we are, that's better. Okay, how's it going? Yeah, it's heading in the right direction. The other thing we haven't attended to yet is timing constraints, but that's going to be beyond the scope of this video, so we will have a look at that at some point in the future, though. I'll do that maybe the next video. The way I approach that generally, I have a top level, a board specific constraints file which sets a bunch of variables, and because wouldn't you know, every platform uses slightly different names for the SD-RAM pins, and while in theory you should be able to use the same set of constraints files, at least for RAM timing, you should be able to use the same set of files everywhere. You really can't. So what I do there is just set some variables to the appropriate pin names, and then you can. Now there should be an SDC file, timing constraints file in here somewhere. Can't see it. I may be looking straight past it, or it may not actually be there. Oh, I don't see it. Well, that's fine, we can find and add it next time. Okay, we've finished building now, so let's have a look at the compilation report. It's just doing the timing analysis now. As I say, we haven't done timing constraints yet, so that won't succeed. But yeah, we look at the fitter report. We're using 47% of the FPGA, so that's good. We've got plenty of room there. If we have a look at the resource section, we're using 56 out of the 66 available M9Ks. And let's have a look at the resource section, resource utilization by entity. If we have a look at there we are, substitute MCU, that's the block which pretends to be the MIST microcontroller, and that's 2297 logic elements. The core itself is 8472, and then there's a bunch of stuff relating specifically to the Chameleon. Just supporting code deals with reading the C64 joystick ports, the CDTV controller, and various other things. So yeah, there we go. I don't have any kind of capture card, so I know it's a bit of a cliffhanger not being able to show you the core itself running, but that's the basic process involved in porting it in the first place. I will now have to do some debugging, and I will also have to adjust the firmware further so that it does actually now try and attempt, does actually attempt to upload a ROM file, because there is a VIC20.ROM that needs to be on the SD card. But I think that's enough for this video, so I hope you found that interesting. Thank you very much for watching, and many thanks to everyone who supports my projects both on Patreon and on PayPal. It really is very much appreciated. That's all for now. I'll talk to you again soon.